Good afternoon, everyone. Welcome back to the afternoon session. The first speaker of this afternoon is Professor Reinhard Werner from Leibniz University, Hannover, on Bohr versus Einstein. Please take it over.
So thank you very much. It's an interesting venue for me. I'm a physicist. Actually, I'm not going to apologize for the Leibniz in the name of our university. But the other interesting thing there is I'm a mathematical physicist working in quantum information theory. So I'm not a historian at all, and so you will see that I'm taking liberties that historians shouldn't, like taking sides in a debate. Of course, if you, well, we can talk that out. So, okay, so these are the two people that we are talking about. So we have Bohr and Einstein. Einstein was a little bit older, also died a bit earlier. Here is a picture of the two of them a little bit at a slightly older age. And some of the famous pictures we have, there are not so many, of the two actually together on the same picture. So this one is particularly famous, sort of like the icon for the Bohr-Einstein debate. So let's maybe put that into a temporal perspective. So I marked here, well, the horizontal line there is 1900. You see the units. I'm a physicist, you see. So one of the remarkable years here is, of course, Einstein's so-called annus mirabilis, 1905, when he wrote 3 fundamental papers. Well, actually more papers than 3, but 3 of them were really famous and changed a lot in physics. And then, of course, in 16 we have general relativity. So he was clearly one of the most creative theory builders we had in that century. Bohr is known for the model of the atom, that is 1913, and also for his notion of complementarity that will actually be also part of this talk. So right away, I think I should comment a little bit on the research style of these two people, because they were almost diametrically opposite. Right? So with Einstein, you could say he was his great superpower, if you want, was this ability to detect clashes between physical principles, also between different theories. So the 3 theories that he was talking about in 1905 were the 3 big theory groups of his day: mechanics, electrodynamics, and thermodynamics. And between any 2 of these, he found a clash of principles and resolved it, or at least addressed it in an interesting way. So, for example, famously, the clash between mechanics and electrodynamics that he detected led to special relativity. Right? And similarly for his work on Brownian motion and on the photoelectric effect, which was one of the founding observations of quantum mechanics. So Bohr didn't work like that at all. In fact, if the Bohr model of the atom, every physics student at the time would have known if an electron is whizzing around the nucleus, as in this model, it should radiate like hell, right? Electromagnetic radiation. And so this was clearly one of the known principles of the day. And what did Bohr do? He said, well, let's just ignore that for a while. Now, this is a move that would be totally against Einstein's grain. Right? He would never have done that. But all the more, but it was successful in a way. Right? So not only did it get the spectral series right, but also worked still for the isotopes, right? for heavy water, heavy hydrogen. And they predicted the correct spectral shifts there. That was a bonus that nobody could have foreseen somehow. And so clearly people saw that there must be some truth in that. And so Einstein acknowledged that and was always very impressed by this work of Bohr, because in a way it was something that he never would have done. So let me go on these matters of style a little bit. I mean, one thing is certainly this whole debate was very polite, and they always had great respect for each other. Actually, in reading up a few things on this for this talk, I came across an exchange of letters when they both got the Nobel Prize, and they were, well, Einstein got it first in 21, but the awarding ceremony they shared in 22. And so Bohr was writing that, it's great that you got it first because I couldn't have lived with you not getting it before me, or something like that. And they were very polite to each other, right? So that's one thing. Their writing style is markedly different. Einstein was brilliantly clear in whatever he said, right? So you can read Einstein and there's no misunderstanding him, I think, or at least very little. Whereas Bohr is almost impossible to read or to extract a clear meaning from. Actually, he said at one point that he thought that truth and clarity were complementary, which in his language means that if something is clear, it can't be right. And so I think that's well, I don't like that attitude very much anyway. So also, Einstein was completely up to the technical tools of theoretical physics of the time. With Bohr, that is a bit dubious. He was always praised for his intuition, like he could arrive at a conclusion without even doing the computation. Well, opinions vary whether he would have been able to, right? So also they interacted with the community very differently. Bohr was very politically minded, right? So, for example, it was very important for him that the theoretical physics community would speak to the outside world with a clear, unified voice, and he didn't mind if it was his, right? Whereas for Einstein was always Einstein always kept out of organizations, and so there's one statement where he said, the only community I ever want to be part of is that of the people who are searching and trying to find out and understand things, and saying in the same quote actually that he believed that was only a handful at any given time, right? So it's a little bit elitist, but anyway. So, okay, so they were different in that way, but they had a common thing also, namely that both were very influential in this process leading up to quantum mechanics. So let me put the timeline on again. So the whole process of guessing and finally arriving at quantum mechanics started maybe in 1900. It's a nicely memorizable date with Max Planck. And then there was all this period of guesswork, and they both had by letters, and actually Bohr gave regular survey talks on the current status of atomic theory, or whatever they called it at the day. So they were both very had strong influences in this community. And then the big thing happened between 25 and 27. It depends on who you talk to and what they put as a starting date, or maybe even the starting place. There is a little booklet around by Carlo Rovelli called Heligoland, where he says it's not just 1925, he can also name the rock where it happened, right? So anyway, I think that's a bit exaggerated. But this was a very, very short period, and within that extremely short period, the theory was formulated and mathematically worked out. Actually, one of the underrated people here is this guy, John von Neumann, who basically created the theory, or well, at least the formalism of the theory, right? Okay, so let us come to the Bohr-Einstein debates. So these are again, the same timeline, the encounters they had. So I will talk a little bit about, in 1927. So that 1927 is after the birth of the theory. Heisenberg's uncertainty paper was out, von Neumann's mathematical structure of quantum mechanics was out, and Bohr was giving a lecture at a conference in Como that Einstein didn't attend. And then they both were a little bit later at the Solvay Congress in 1927. And there's a remark by Einstein that I will comment on about the meaning of the wave function. So this is the first meeting, and they had big discussions here. I call that the round one of the Bohr-Einstein debate. Then there's round two, which is in 1935, triggered by the paper by Einstein, Podolsky, and Rosen, short EPR, about, well, problems he saw in quantum mechanics, and very famously a reply by Bohr. I will definitely comment on that. So these are the two main events of this Bohr-Einstein debate. Okay, so let's have a look at the topic. So what was the debate about? And one way to put it is to say it was about the, one of these principles of Einstein that he was so great at, right? So one of the way he wanted theoretical physics to work. And this could now be summarized under this heading of local realism. That's actually a term that was coined later, but I think it fits pretty well what Einstein wanted. And so the idea is that if you build a new theory, and they were just building a new theory, quantum mechanics, then the first thing you should do is find how to describe your system. What are the variables, the mathematical objects that you use to encode what the world is like, right? And this kind of description should give you, provide a language so you could talk about the real factual situation in some region of space-time. That's actually a phrase that he used, so it's in quotes. Not that early, but he did use it, right? So, and part of this idea is that, of course, Einstein created relativity. So this causality idea was always there. That is, if the real factual situation in one place should not depend on what somebody else does far away, right? And relativity has a very sharp notion of what it means far away. That means that no light cannot be connected with a light signal, right? So, so there is a locality part of it, and of course also you would like to see dynamical laws that tell you how the state changes, right? Okay, so this is the ideal of local realism, and one has to say that all of classical physics, classical is of course just a term to say pre-quantum in this context, right? So all pre-quantum physics works like that. So it was an abstracted principle from the way all physics at the time worked, right? So it was not just invented for the purpose. But he had this. He would be one of the few who would actually see that as important and formulate it and say that this is how things should work. Okay, so these variables that you have to find might not be totally obvious. So this Einstein's realism, if you want to call it that, is not naive in the sense that you just look at nature and then you see how to describe it or so. Right? You would have to just invest some serious work. So in his later work, when he tried to build an account along that pattern for quantum phenomena, he writes to Schrödinger that he's now trying overdetermined systems of nonlinear partial differential equations as a mathematical background that might do it. So he was really thinking about something that you have to, some mathematical structure that you have to create, and that might be totally non-obvious to the eye, right? Okay, so this is the quote. The reality is not handed to us, not just given to us, but it is like a riddle. We have to uncode it. You have to find the right description for it. Okay, so the counterposition to that would be this maxim that theories should be built on observable facts. Now, to begin with, this is not a direct contradiction to the other one. But in quantum mechanics, it sort of is, because we don't directly see the quantum particles. So there's no level where you can see the description of a reality and what we see of it are not somehow obviously connected, right? And of course, in some way, the whole debate is about that. So it's not a direct contradiction, and it is actually a very early position from the Copenhagen side, if you wish. So this is actually Heisenberg's principle with which he starts in 1925, that the theory should be built on observable facts, and at that moment, this is directed against Bohr's model of the atom, because the orbits in the atom are something that you can't see directly, right? Because it's, you don't, if the atom doesn't radiate, how would you know that the electron is going around in a circle? So he says we have to look instead at the interaction with light, and he comes up with these matrices, right? So, and then also later in 27, he actually follows Einstein in his work on relativity. So the way the first relativity paper is written, he says, well, if we look at the idea of simultaneity, equal time relation, and we do this under the conditions that there is an observer-independent speed of light, that is the same for every observer, how would synchronization then work? How could this concept even work? And if you work a bit, well, quite a bit, then you end up with relativity in a pretty straightforward way, right? So this kind of analysis that some people would also associate with the style of Mach, Ernst Mach, he came up with relativity, and Heisenberg is trying to be the quantum Einstein, right? So definitely in the 27 paper he does that very explicitly. 27 is that's a paper on uncertainty relations. So there's this passage in Heisenberg's autobiography where he relates the story that he met Einstein after doing this work, and so the young man, he was, how old was he? Like 24 or so, right? So he's going to Einstein and say, I applied your principles and I came up with this brilliant new theory, right? And Einstein was not impressed. He said, well, this is good. I may have said something like that you have to start from observable facts, but was kümmert mich mein Geschwätz von neulich? So what, no, he didn't say that. But I say a lot when I don't think this is true at all. Instead, he says, the theory decides what can be measured. Now, if you want to put that in this context of this debate, in this idea of local realism, then what he's saying is, if you understand the right variables of the theory and the dynamics of the theory, there is no separate measurement problem. This will automatically follow, right? You just follow the dynamics of the process that will involve also the measurement devices, and therefore everything is clear, right? You don't need any starting point from the measurement process. Okay, so this is actually what you could call the classical view of measurement. A measurement in that classical view is something that uncovers a property of the system that is already there somehow. And that is something that, well, in quantum mechanics we have become wary of, right? So, but that is basically what is behind this. Now, also in this counterposition is Bohr's notion of complementarity, which is that what classical concepts can be applied to a certain system? Like, does it appear to us as a particle or as a wave? That is, in the early days, that is really the distinction, is decided by the experimental setup. If we make an experimental setup that is wavy or sensitive to the wave nature, there is no sense to even talk about the particle nature of the particle properties of the system, and conversely, right? So the experimental setup decides. So this is exactly this start from the observations, from the operational description of what we do in the lab, and that sets the concepts that we can use to understand the system. And of course, this introduces a fundamental role for the observer. In Einstein's local realism picture, the physicist doesn't appear in any form, right? You talk about the world, and you don't care whether there are physicists around or not. Here, in some sense, you have to care about it. Okay, God, I'm late. So round zero is this story about what is psi, and this was at the Solvay Congress. It's a short remark that he makes and says there are this wave function that came up in the Schrödinger's equation, was one of the key mathematical elements of the theory. How do we understand it? And he presents two options, and they are pretty much along the lines of this debate. One is, well, this could be the description of an individual system, pretty much in the way like the variables that we have been looking for to describe quantum systems. That might be this wave function psi. Einstein always calls this the orthodox view. This is what he perceives the Copenhagen people are saying or are trying to do. And he has a problem with that. I have to go a bit faster now. So then if the wave function has something to do with the clickishness of the system, like the ability to trigger a detector, then if you have already seen a click, then everywhere else it must be zero. And this is kind of a non-local effect, but that only is a non-local effect if you believe that the wave function is a thing somehow, is a real physical field in the sense of local realism. The counterposition to that is an ensemble view, where the wave function is something like a probability distribution. And well, it describes a set of similarly prepared systems. So in that case, the collapse is just an update of a probability. You can do it in the evaluation stage of your experiments maybe decades later. It's nothing that happens actually in the lab. Okay, so just for a cartoon, in the ensemble interpretation, the psi is something that relates to the preparation of the system. Of course, there will be a measurement to complete this whole experiment, but the psi would be about the preparation. And this is basically the minimal statistical interpretation that is quite sufficient to do everything in quantum mechanics or quantum information. The individual state interpretation puts it to the particle. So there is electron Joe with his own wave function coming along, right? So this is the different way of thinking. It's about the individual state, the individual system. That's what he calls the orthodox view, and many physicists are fuzzy about this distinction, still now, right? Actually, one recent debate calls this the epistemic view because it has something to do with what we know about the system. You could phrase it like that. And this is about what the system is. That would be the ontic view of the wave function. Okay, so I'll go a bit faster. Here's a quote from Einstein that really makes that distinction. Just very briefly, of course, he famously said that God doesn't play dice with the universe. And that is related to this thing that whenever you invoke probability, a probability distribution is never a physical field. It's something that depends on the whole way you set up your experiment. If you look at the probability distribution for a Brownian particle to be somewhere, it depends on where you started it. And it will be updated if you've seen it on the way in some other place. But nothing changes at the point where you're evaluating the probability. It's always about the entire situation. And so this introduces some kind of a subjective element that Einstein feels has no place in a fundamental theory, although he's much better at probabilistic theories than all of his colleagues, right? In 1905, he wrote one very probabilistic paper, right? Okay, so Bohr said to this, but it cannot be our task to tell God how to run the universe. This is actually one of the things that I wholeheartedly agree with because, yes, Einstein was trying to implement a physical principle, but then sometimes we do have to give them up when we are forced to by nature to do that. Well, they say God, but it really it's nature. Okay, so the Solvay Congress debates. I'll go quickly over that. So the narrative here that you find easily is that in these congresses, Einstein would, this is not in the proceedings because it was all over meals, right? Or about other meetings outside the conference room. So for breakfast, Einstein would propose a thought experiment refuting uncertainty, the uncertainty relations. And then by the evening, Bohr would have a refutation and they would talk about that, right? Now this account is on the one hand by Bohr's own long account in the volume put together in '49 for Einstein, and there's a short paragraph in Heisenberg's autobiography describing it, and the only contemporary source that I know, there may be a few more, is a letter from Ehrenfest to Goudsmit and Uhlenbeck. I've quoted it here, so it actually tells the story. Let me just go over it quickly too. But the perception that Bohr won this debate is basically from these sources. So they're written by the winners, right? And I know that as a student, I read this stuff. I said, what the hell are they doing? This is like like a non-English person going to a cricket game, right? Everybody cheers, and you just don't know why, right? And so this was, I was actually confused about this, and I think I can tell you that a little bit better now. It is about what they're doing here. They're playing a game of semi-classical physics. And that has some rules, so it has nothing to do, or very little to do, with quantum mechanics. That is what was confusing me. Right? Like quantum mechanics is post-26 quantum mechanics, of course, for me. And then Bohr had, well, so you would mix wave pictures and particle pictures, and somehow arbitrarily switch between the two, and connect them with the Bohr relations. That was sort of the style of it, right? And then, yes, you can weasel your way through. That is what Bohr actually did, quite successfully and not stupidly. But really, this is a theory mix that is less than half-baked, right? It doesn't give you anything like an interpretation of the modern quantum mechanics, that is the post-26 quantum mechanics. And it did allow Bohr to remain a quantum guru without actually learning the new stuff. That is maybe a bit harsh, right? But there's actually very little evidence that Bohr mastered modern quantum mechanics ever. So he was always staying in this so-called old quantum theory. Okay, so yes, so Heisenberg also worked like that, and not very successfully. Oh, well, okay. So my reading now is that Einstein was railing against this inconsistent mix of things, where you would have like, this is like double think, right? You can use both pictures, thanks, but really there's no criterion for when to do what. So okay, so let us go to EPR. So this is the paper, and this was written by Einstein and Podolsky and Rosen to combat this view that the wave function is like a variable in the sense of local realism, that it describes an individual system in every way. So this is what they call completeness. Right? The completeness would be like the role of this variable as such a description, as in local realism. And so here is the wave function is cited in the abstract and so on. And so the new element in this is that they look at correlation experiments, and that is very clever. That is definitely what we're using it from, what we are using these days in entanglement theory and quantum information theory and all that, right? So, so if you pick the right source and the right measurements here, then you have that they're maybe fully correlated between Alice and Bob. That is, whatever Alice measures, there's a corresponding measurement on Bob's side, so that these will be 100% correlated in their outcomes. So in other words, you can find out stuff that would happen at Bob's by measuring at Alice's side. This completely eliminates this sensitivity, this perturbation aspect, this actually the uncertainty relations. And so this is why this is an interesting situation. The argument is that in this situation you can compute what kind of state should describe Bob's system, and you think that this should be a real ontic state describing the real factual situation there. But then this choice would depend on what Alice was measuring. So it depends on a faraway thing. So it is not local realism. Right? So that is basically the EPR argument. Of course, there's more to it. But so how was that done in the community? Well, I'll go over this quickly. So there was this nice phrase by Schrödinger that they all found it wrong, but only because they had learned their Copenhagen credo in unum sanctum. So my Latin is a bit rusty, actually like 60 years rusty. But it would be una sancta ecclesia normally, right, in the credo. But here it's male, so it really says they had all learned their credo according to the saint who can only be Niels Bohr, the one saint, right? Anyway, so this is a letter to Pauli, and Pauli writes to Heisenberg, Einstein once more made a public statement about quantum mechanics. It is well known that it is a catastrophe every time that happens. I want to grant him that if a beginning student would raise such objections, I would consider him fairly intelligent and promising. How patronizing can you get, right? This is really... And then he suggests to Heisenberg, whom he's writing, that somebody should, you know, take care of that, right? Clarify authoritatively that this is nonsense. And Heisenberg's, so I don't know the response to this one actually, but the Heisenberg's response is known. So he said, well, Bohr is already doing it. So here's Bohr. Bohr's reply appeared in the same journal with the same title and the opposite answer, which is, let's say it's a level of polemicism. What's the word? Polemics. It's a level of polemics that is definitely very unusual in a physics journal. Right? You don't have that. This is really bad style. Right? You wouldn't actually nowadays people would just cross it out. But this was Bohr. Right? So he got away with it. And here is a description of his then assistant Rosenfeld, what he did. Right? So Einstein's problem was reshaped and its solution reformulated with such precision and clarity that the weakness in the critic's reasoning became evident. And their whole argumentation, for all its false brilliance, fell to pieces. It was impressive to watch him thus at the height of his powers. He was particularly well served on this occasion by his uncommon ability to go into the opponent's views, dissect his arguments, and turn them to the advantage of the truth. I don't know how you feel about that. I think this is utterly embarrassing hagiography, right? So actually what he's suggesting is that false brilliance means that there were intentional deceiving in this other paper, and they were not after the truth, right? So which is, yeah, I think this is, Rosenfeld should be ashamed of himself. Now, actually, this is the abstract of the paper. So Bohr claims an essential ambiguity in the paper. Actually, he doesn't name an ambiguity in the paper itself, and he uses the word essential only to emphasize places where he has no argument, right? Then of course he is advocating complementarity. Actually, three quarters of the paper are a lecture on complementarity. And now I would like to draw your attention to this last line here. So he says that complementarity fulfills certain demands, but he doesn't say that it fulfills the demands. It would seem to fulfill. Well, not even that. It would seem to fulfill, but only within its scope. So he was stepping on the rhetorical brakes 3 times, right? And then he pulls out the sledgehammer and says, well, this is about all rational demands of completeness. So who wants something else now is just being irrational, right? This is typical Bohr, right? So this mixture of pontificating and extreme caution in the formulations. So actually, he completely ignores the new aspects, actually transforms them away in a footnote on page 1, the only place where he actually uses formulas. Totally misses the point of the paper, of the APR paper. Actually, from the response, it's not clear that he read the paper even. We know he did, and he probably thought about it a lot because his whole complementarity philosophy changed in 1935. Yeah, so he clearly took a message there, but you wouldn't know from his response. So he has this lecture, and actually, one way to highlight the quality of this writing. In the collection by Wheeler and Zurek, right, Quantum Theory of Measurement, or so it's called, a red book that was on many shelves, 2 pages had been transposed in the reprint, and nobody noticed. So this is just as an indication of the stringency of this argumentation. Okay, so, but the effect of Bohr's reply was this. Case closed. And actually for 30 years nothing happened. Well, almost nothing. I could name a few things, but really nothing. And the reason is that, you see, Pauli's suggestion, somebody should get rid of that for us. That is exactly what happened. This was the golden years of quantum mechanics. All these young, highly motivated, intelligent people who were just getting their Nobel Prizes by applying the new theory. They were just not prepared to listen to the old man who say, well, I have my doubts. Right? They just wanted it put away. And that's what happened. So after 30 years, we have this guy. And actually, this closes the debate. So this closes the debate about local realism. So actually, his argument is very elementary. It eliminates not just the psi kind of ontology, right? Psi as a mechanical variable, as a local realistic variable. He kills any kind of local realism, provided a certain quantum prediction was verified experimentally. So he actually opens up the possibility of an experimentum crucis, which is very, very rare in science, as all the historians here will certainly confirm. Right? It's very rare that you can make one experiment definitely deciding a matter. This is one, and that is the last year's or this year's Nobel Prize for actually experimentally doing just this verification. Okay, so I'm at my summary here. So I've restated the question. And so this is my, about the people, his contribution to this, Einstein's contribution to this debate was to even state the problem clearly. And this he did very efficiently. And also made his contributions like the EPR paper. Bohr was actually not part of the debate in some sense. He was the figurehead for this whole quantum community that was emerging. They had delegated this whole debate to Bohr. And he did it, well, maybe to the best of his abilities, but they were not great. And so of course, this is a common debate now, like how much can we credit to Bohr? How much understanding was there actually? There are some very negative books like Marabella's Quantum Dialogues, maybe some of you know that. It's very bitter on Bohr. Actually, I spent a couple of hours at Blackwell's yesterday, and on display there was a book on Bohr's vision of physics by a guy called Perovich that I didn't know before, and I had a look at that. I'm all prepared to look at more charitable readings of Bohr, but it's hard to do, and it's very frustrating if you do it yourself. Okay, so the outcome of the debate in my summary is in round one, the general perception is Bohr won. I would say in the long run, this semi-classical complementarity that we're debating is now dead, really. You cannot do anything sensible with it, as if you ask me at least. Now, round two, the 35 round, was basically ignored by everybody. So the public perception wasn't even there. But in the long run, clearly, the result is that Einstein's view of local realism was refuted, was shown to be inconsistent with experiment. Yeah, I'll leave it there. So thank you very much for your attention.
Thank you very much. So wonderful talk. In the middle, please. The gentleman in the middle.
Thank you for your talk. Very, very enlightening. Would you agree that Rosenfeld's quote that you gave was very typical of him? Very typical of Rosenfeld, sorry. First he was a Marxist, and so he was completely certain in his political views, and he took that certainty over into physics too. He absolutely adored Bohr, and anything Bohr said was definitely correct. And anyone who didn't believe it, and he said this many times in letters or in print, was either completely mistaken or a fool. He more or less had a Newtonian view of opponents.
Rosenfeld was actually particularly bad about that, but also many other people in the community. There's this horrible incident where the young student, or a PhD student of John Wheeler, came up with what we now call the many worlds interpretation, right? So Everett was sent to Copenhagen to get a blessing, which they weren't actually interested in. So Wheeler dropped Everett in a really, really bad way, right? So this perception of Bohr as a great saint who would sort of residing over everything and so on was very widespread. So books like Marabella's are a bit of a pendulum going all the way in the other direction. The truth is bound to be somewhere in between. I'm also a little bit on the far side in the criticism of Bohr.
In the back, again, middle, the third from the back. Yes.
Thank you for that. That was fantastic. Correct me if I'm wrong, but I understand that towards the end of Einstein's life, he spent a lot of time working on theories of everything, unified field theories. Sorry. I understand that towards the end of Einstein's life, he spent a lot of time working on unified field theories. And my understanding is that this wasn't looked upon particularly favorable by a lot of the rest of the physics community.
Certainly true, right? But what it means by unified field theory is actually unification of electromagnetism and gravity. As far as I know, it doesn't involve the quantum side. But this was another research program, finding a local realistic description of quantum mechanics that was up to the end of his life. You could have thought it's a reasonable program. I think with a bit of more, you know how it is. Sometimes if you have to, when something doesn't work, you have to turn around and try to disprove it. Had he done that sometime earlier, he would have come up with a bell-type argument, maybe. But he didn't, right? So he was guilty of not trying to shoot it down, which is, I think, a reasonable, after a few decades, is certainly a reasonable thing to do. But until his death, Bell really completely kills this idea. And I think he would immediately have accepted that and seen that, yes, you cannot do this, right? But the unified field theory is a different project. Yeah.
Okay, the second from the back, please, and then next, the gentleman in the middle.
You talked about the clarity of Einstein's writing, but I've heard that if you really want to understand relativity, you don't understand it from reading Einstein. You understand.
Sorry, can you repeat the last part?
You talked about the clarity of Einstein's writing,
yes.
But I've heard that if you want to understand relativity, you don't study it by reading Einstein, you study it by reading other people who read Einstein and then explained it more clearly. So can you comment on that? Okay,
so relativity is something that has been done many times over and explained from different point of views. Like there's a beautiful little volume by David Mermin called It's About Time, right? Okay, very nice. It's also a good book. So many people have done that, right? And there's a long row of people who have explained relativity in their own way, slightly differently from Einstein. But I would suggest you read the 1905 paper. I think this is quite clear. So, and also in the statements about quantum mechanics, to my reading, it leaves nothing to be desired. It's quite clear what he wants. So, yes, relativity is actually quite easy to understand. And of course, there's also a big pedagogical literature about it. And yes, you could say that maybe Einstein is not the ideal presenter of it, but I think it was pretty good.
So the third from the front first, and then go to the back. That last question.
Hi. I wonder if you could just say a few things about what you, as a physicist, think that the death of locality means. I mean, from a philosophical point of view, I tend to think that it means the death of our sort of naturalized concept of space.
Okay. First of all, I did not say the death of locality. I said the death of local realism. Yeah. Locality is alive and kicking. So actually in this whole, I've been touring the country, various countries actually, in explaining the Nobel Prize. And one thing that you have to repeat again and again is that this so-called spooky action at a distance simply isn't there. Right. There is no action at a distance in this whole setup. You only get a superluminal signal or any kind of signal if you use the wrong theory, which is a local realistic one. And then you see that there would have to be a signal. But Einstein's position is that no, this just shows that's the wrong theory. So Einstein was not refuted by these experiments in that sense. Right? He never made a wrong claim about it. It was a research program that he tried to pull off. We now know it's impossible. And of course, all this whole set quantum view of things is confirmed. But there is no action at a distance here. Actually, Einstein called it a spooky action at a distance. That was in a letter to Bohr. Eine spukhafte Fernwirkung. Right? And the German phrase, even more than the English one, does not suggest Halloween spookiness. It says weird. Right? Actually, it's not actually there. Einstein knows full well, and he's writing to his friend Bohr, who knows equally well, what he means by an action at a distance. Something that allows you to send a signal. And they're completely aware from the outset that quantum mechanics does not contain this. There's no way to build a telephone with superluminal signals on the basis of all this. So this is why he calls it spooky. It's just spooky. It's not even an action at a distance. Right? So it's not a proper action at a distance. It's just a spooky one that seems to be there when you use the wrong theory. Sorry, I was... Is that clear enough?
So what does that actually mean? What does it actually mean then? What does it actually imply for physical reality, if you like?
So well, first of all, it completely kills this notion of systems completely described by their properties. And because if you do that, you would get, I mean, this would be the classical part of the realistic part of local realism. If you do that, you get spurious action at a distance in your theory that you then have to explain isn't even there, because everybody knows it's not there. Right? It's experimentally and theoretically, everybody agrees. There is no action at a distance. There's no way to build a signal. So you get, when you use the wrong kind of theory, like certain Bohmians do, then you get some kind of non-locality in the sense of signals, but only in this wrong theory. So you have to live with that and realize that you cannot describe quantum systems by a complete list of properties, and that everything you find out by measuring is not just uncovering something, but introduces an interaction in this interaction your result will be generated. But it destroys whatever other properties the system might have before. So it's actually not sensical to even talk about these properties. Or not helpful. If you wish, you can, but it's not going to be a part of any explanation. Sorry, it was a bit long.
Let's move on to the last question.
Thank you. That was actually more or less answered my question. I just wanted to say thank you for the fascinating presentation. You started by showing us how absurd Bohr's approach was actually, and how reasonable Einstein's criticism of this situation is. But unfortunately at the end you say, well, Bohr is right and Einstein is wrong. So even though Einstein's criticism and everything was justified and reasonable, he was wrong, and Bohr was right all the time, even though nobody actually understood what he was saying.
Okay, I would have to go over a few things again to respond to that. So there is early Bohr with this very simplistic complementarity viewpoint, which is basically about waves versus particles. And there is a later version of it, actually in response to the 35 paper, where he says, well, you always have to use classical concepts even if it's just to communicate the results of your experiment. You have to use a classical language. There is no quantum language that you could publish in the Physical Review. So, this is something that nobody can, I mean, everybody has to agree on that. That's simply true, right? So, but this milder form of complementarity is something that we're actually using all the time now. So this is this operational view of quantum physics where you do start from the devices. So in that sense, yes, Bohr was right. Not the early Bohr, certainly. He had completely crazy ideas, some of them. But this part that we are taking over, it's like Heisenberg's program of starting from observable quantities, but much more radical than he was. So we went this way. And it works perfectly and has been working for 100 years, right? So in that sense, yes, Einstein's vision, we had to give up this principle by Einstein. But Bohr was not very helpful in making that transition. Okay, in some sense he was right in the end, but yeah, he didn't contribute much to that. Yeah.
Okay, I think we should move on to the next speaker. So maybe during the coffee break, please ask the question. Let's thank the speaker again.